I think that the topic of representation is possibly the most important in computing and computer science, because if you think about it, if you don't know how different types of information are stored inside the computer, how do you manipulate them? How do you do something like a shift cipher, for example, on text, or how do you manipulate an image, as we looked at in the previous video? And in this case, we're going to have a look at how sound is represented. So I used to do this demonstration in my lessons using Audacity, which is a good free application to download and edit sound. But obviously, if you only want to do this, that's a lot of bother to go to, and not everybody uses a device upon which you can install Audacity. People use things like iPads and Chromebooks these days. So I made this page, and if you use this page, there's links to the pages that I'm going to use in the description below the video. The first thing it will do is it will ask you whether you give it permission to record the sound. So the first thing I'm going to do, so it's already done that for me, so I'm going to record a sound. So if you want to record a sound, you just click on the button here. Testing 1 2 3, and then you click stop when you're happy, and what it does is it shows you a recording. So if you don't know anything about sound waves, so school students might have done this in physics, but basically a sound wave can be represented by a line like that. The height of the line represents how loud the sound is, the amplitude, as you call it in physics, and the frequency with which the wave oscillates, and because it's a bit compressed here visually, it's a bit difficult to see that represents the frequency. So how does the sound get recorded and used in the computer? So in this video we're talking about wave files. So there are alternative representations, and if you look on the website there is a link, I'll put it in the description as well. So things like MIDI files are a different way of recording it. That's used by electronic instruments, sequencers and so on. And also pianolas and fairground organs also use that kind of idea. So we've recorded our sound here, so you can see kind of what's going on. I said testing 1 2 3, so that's probably testing 1 2 3. So you can kind of pick out words, but if we scroll down, what we can see, I've added a couple of sliders here. The first one allows you to zoom in, and it zooms in about the middle. Okay, so and it'll tell you at the bottom the time period of the amount of sound that you can see. So that's 0.2244 seconds worth of sound. So you can keep zooming in. If it's not, if the bit you want isn't in the middle, you can use the other slider to just move it over a bit and center it. So you can keep zooming, and you can keep zooming and keep zooming, and at a certain point what will happen is you'll see these red lines appear, and those red lines are where the computer has sampled the sound. So what the computer does when you record sound is, with a fixed frequency, and on this particular page it's 48,000 times a second, and that's why, in fact, it mentions that in the description at the bottom, 48,000 times a second the computer measures the height of the wave, and that's where the red lines represent the points at which the sound is measured. Notice that they're evenly spaced. And you can get an idea of how frequent that is by, again, looking at the duration of this sound. So in here, we've got 0.0035 seconds of sound, and there are 166 samples in that amount of time. And you're probably aware of that kind of quality file size trade-off. The more often we sample the sound, the higher the quality, but obviously that will result in a bigger file. So that's recording. You can also download the recording. Note that it's currently compressed. I couldn't find a way, or haven't yet found a way, of being able to download an uncompressed file in all of the different browsers. So the benefit of having an uncompressed file, of course, is that you could download it, you could check the file size, see if my calculation is correct, because it tells you how much data. So what you could do is you could zoom out and it would tell you, in fact it does tell you how much data is in the whole of the recording. Okay, so thinking about how the sampling takes place itself, does it matter how often you sample these sound waves? 48,000 times a second sounds like quite a lot, but that is quite a common sampling rate, that's known as. So digital radio and television broadcasts, DVB, so Freeview, FreeSat, are sampled that often. CD sampled slightly less often, 44.1 kilohertz, 44.1 thousand times a second. And in the image video, we talked about metadata. So what the metadata would include in a sound file is not just the measurements of the sample, because each time the sound is sampled, so if we just zoom back in again, the height of those bars, or the height of the sample, the amplitude, the volume of the sound effectively, would be stored as a number. So that's just a length, isn't it? So that can be stored as a number. But just as with images, just knowing what the pixels are doesn't help us to reproduce that sound. If we didn't play back those samples at the right rate, then we'd have a different sound, wouldn't we? That's a bit like, if you're familiar with vinyl record players, if you put on your record at the wrong speed, it doesn't sound right. Old tape recorders were the same. So it's important that we play them back. And so metadata for sound would include things like the sampling frequency and also how many bits in each of the samples. So that's a recording. You can see what a recording looks like if you kind of visualize it and what the numbers would be like. There's also a page on sampling. So does it matter how often we sample the sound? So what this page does is, again, it's got some sliders at the bottom, is it shows you a kind of representation of a sound wave. So the black line is like a sound wave, and the width of the rectangle in that case represents 1 second. So currently that audio wave is a 1 hertz sound. Now obviously that wouldn't be audible, but it's just an example. And what we're doing here, the red bars represent the samples. So we measured in that period 10 samples. So our sampling rate is 10 hertz. And so the thing to look at on this page is how closely the shape of the bars fits the wave. So we can see, if you kind of sit back or squint a bit, you can see that does represent that wave, but it doesn't fit it perfectly, does it? So it's a bit like those questions in maths where you have to work out the area under the graph by splitting it into a series of rectangles. The more and the smaller rectangles we use, the better the fit will be, and we do that by sampling more often. So if we increase the sampling frequency, what we'll see is, because effectively we sample more often, the samples will be a better fit, and if we go right up to the end, we'll see that that's an almost perfect fit to the sound wave. So how often do you need to do it? Well, let's increase the frequency a bit here. So obviously the higher the frequency that you want to record, the more times you need to sample it, because if you only sample once per wave, or in fact actually we're sampling twice per wavelength there, aren't we? So if we only sample once, then you're going to hit the same point on the wave each time, so it's not going to vary. If I sample twice as often, so here we can see the audio wave is 2.5 hertz and the sampling rate is 5, so we're sampling twice as often as the wave oscillates. We're getting 1 up and 1 down, so we can see that it's changing, but it's not a brilliant fit, is it? So the important thing there is we need to sample at least twice as often as the frequency of the wave. You can get slightly strange things. So if I increase some of these values here, notice what happens as I adjust the sampling frequency. So sometimes what you get is, so we can see that the wave's going up and down there, but if I increase the frequency, what's going to happen? We get to a point where actually it's if you were to do a kind of line of best fit through the samples, there you go. So that's an interesting example, isn't it? So it looks like the wave is going, well, it's kind of about 2 hertz, isn't it? Kind of a wave. So that's not properly representing the sound. It looks like the samples are representing a different frequency from the actual wave. And notice there that actually the sampling rate is I'm just in the wrong one there. So if we go less than, so if we just put it in the middle, let's make it 10. It's a nice round number. So if we sample it like there, for example, we can see that it's going up and down with a completely different frequency from the wave, and that happens quite often if there's a mismatch. So there, for example, if we were to play back those samples, we wouldn't get anything like the original wave. So that's important. The other thing is the number of bits. So when we looked at the images, we said if you have fewer bits, you get fewer colours, and that can lead to an interesting kind of solarization effect. So the same thing is true of sound. So I'm going to reduce the frequency. So we've got a good number of samples. There we go. So something like that. What about if we reduce the sample size? So at the moment, we've got 8-bit samples. So there's 256 possible heights for each bar. And so, in fact, let's go higher still. So let's increase the sampling rate. So we've got, that's quite a good fit, isn't it, those samples? But what about if we reduce the number of bits per sample? So what that's going to do is reduce the possible number of possible heights for each of the bar. So if we reduce to 7 bits, there's only 128 possible heights for the bars. That's not looking too bad. That hasn't made a lot of a difference. If we reduce it further, again, not looking too bad. Just like the colours, a small decrease doesn't make a drastic effect on the sound. But once we start getting down, so 16 possible values, not too bad. We can see there, though, now we're starting to get some kind of corners, aren't we? There's only 8 possible heights that those bars can have. So it's getting quite stepped. And as we reduce the number of bits representing each of the samples, it's reducing the resolution effectively, isn't it, of the sound. We can see it goes up in steps, and that's going to reduce the quality of the sound. That's not going to be such a good representation of the thing that we've recorded, although it is going to make the file smaller. And obviously, if we go down to 1 bit, that's literally 2 possible positions, up or down, where everything's going to become a square wave. So those are the factors to think about. So what the sampling frequency will affect how good the recording is, and sometimes if your sampling frequency is wrong, you might end up with just a completely different representation. And the number of bits as well. So the number of bits can kind of coarsen the recording, or the number of steps. So where does this information appear? Where might you see this? So CDs, for example, they sample they use 16-bit sample size, and so that's 65,536 different levels, and that's considered hi-fi quality, sampled at 44,100 times a second. So don't forget, the highest thing you can record is half the sampling frequency. So that means CDs can replay sounds up to 22 kilohertz. So that's pretty high. That triangles and things should be fine there. But if you're interested in streaming, you can stream at a higher quality than that. So certain services like Tidal, for example, or especially Quobuzz, the French streaming service, you can stream tracks recorded up to 24 bits. So that should allow you theoretically, greater difference between the loud bits and the quiet bits, called dynamic range. And you can also sample. You can also download or listen to tracks sampled at 192 kilohertz. So that's a lot higher than CD. So half of 192, that's 96 kilohertz, would be the highest sound. Now that's way beyond the level of human hearing, but there is some research to suggest that although you can't, actually hear them consciously, you can detect when those things are missing. So the jury's out on that, whether it's worth the extra data to go beyond CD quality. But if you can sign up for a free month and try it if you're interested. So that's where that information would appear. So if you're comparing, downloads and things like that.